Now I want to talk about effect sizes or unitless measures of association when we're dealing with this kind of regression model with the ANOVA framing device layered on top of it. Here's the example model that I've been working with. Price is the response variable, and I have the interaction between material and transport predicting price. And this is just the standard regression summary table that we've looked at a bunch of times right now. This is a regression model, so you can use all the same effect sizes or unitless measures of linear association that you would use for any regression model here. See the previous videos for details about that. But when we're presenting it in this ANOVA fashion, using the capital A ANOVA function from the car package to get sensible defaults for the main effects, we have a couple of additional options for effect size measures, or unitless measures of linear association. The most commonly used effect size for an ANOVA f-test in psychology is partial eta squared. The first column of the ANOVA table shown on the screen illustrates the sum of squared deviations accounted for by each term in the model. Recall from the previous videos that regression is based on minimizing the sum of squared deviations, and the concept of variance itself is based on squared deviations. This sum of squared deviations is often abbreviated when we're talking about it to sum of squares or just sum squares, and that's why it's abbreviated sum SQ here. The residuals row of this table shows the sum of squared deviations from the fitted values in the full regression model, from the regression line, with the interaction in that model. The other rows in the table can be used to understand how much of the original variance in the response variable is explained by each term. Partial eta squared is the sum of squares value for the predictor divided by the sum of itself plus the sum of squares value for the residual. It represents a proportion of variance explained by the predictor, specifically the proportion of the variance that would have been unexplained if not for that predictor. To illustrate, I'm going to calculate one manually here, but then I'll show you a way to calculate it automatically. I'm going to take this capital A ANOVA table from the car package, and I'm going to assign it to a new name so that I'm storing it as an object in my global environment. And that object is called ANOVA table. And then I can use square brackets to retrieve particular values from this table. This is the formula that I'm using. ANOVA table square brackets 1, 1 retrieves this number from the table, 12,165. And 4, 1 retrieves this number from the table, 231,958. This whole formula takes 12,165, that's like a measure of the variance explained by material, and divides it by 12,165 plus 231,958, this denominator term, which is like a measure of how much variance would have been unexplained if we did not include this term. And the result is 0.0498. This is a measure of effect size, a unitless measure of linear association between material and price in the context of this model. If you don't want to retrieve values from the ANOVA table yourself and calculate a partial eta squared by plugging those values into a formula like this, there is an option. There are several packages that can help you calculate these automatically. I'm going to show you the one from my set of miscellaneous functions. And this also includes partial omega squared. Remember, you can get the miscfunctions.r file from this URL. And if you download it and included it in your working directory, then you should be able to run source on this file name to get the definitions of all of those functions loaded into your current workspace. One of those is called AutoANOVA, and it allows you to specify a model formula that's going to be used in a regression model and a data frame to find those variables in. And it gives you the type 2 ANOVA table from the car package with some extra columns added in and some other extra information that you can learn more about if you look at the documentation of that function when you download miscfunctions.r. The point is, here's partial eta squared. It's that 0.0498 value that we calculated manually up here. And it also gives you the partial eta squared for the main effective transport and the interaction term. It also gives you an additional column with partial omega squared in it, and you'll see that these partial omega squared values are slightly smaller than the partial eta squared values they correspond to. Partial eta squared is just a proportion of variance explained by the variable in question in the observed sample. It does not attempt to represent the best unbiased estimate of the proportion of population variance that might be explained by the variable. Partial omega squared compensates for this tendency to overestimate the population variance explained. You don't need to know the details about how it's calculated. It's slightly more complicated than partial eta squared, but it is useful to know that it's basically a better estimate of population variance explained than partial eta squared, but much less commonly used. By the way, if you're using the error term from the same regression model, then partial eta squared is the square of the partial correlation coefficient that was covered in the videos about regression from a couple of weeks ago. In this case, it's not exactly equivalent to the partial correlation coefficient because the main effects come from one regression model and the error term comes from a different regression model in this type 2 output. But if it wasn't for that, partial eta squared would be the same as the partial correlation coefficient squared.